I would like to talk to you about exceptions in periodic trends and electron configurations. Speaking of which, electron configurations are actually very useful for explaining apparent deviations and exceptions in periodic trends. So why don't you pause the video and write out the electron configuration for scandium, atomic number 21. Depending on which method you used, you should have written out the following. Now let me tell you something. Experimentally, it has been shown that the 3D sublevel electrons spend most of their time closer to the nucleus when compared to the 4s. Also, with ionization experimentation, it has been shown that the first electrons to be expelled or ejected are in the 4s. So, based on convention, students are typically taught this, when in reality, shouldn't it be written like this, with the 3D filling first, followed by the 4s? This is something that I will leave up to you. I will accept either form. You may want to ask your teacher what they prefer. This is a very powerful discussion to have. What is shown to be true is 3D1, 4s2. Again, I'll accept either form, but I felt that I had an obligation to teach that to my students. Let's look at these two families, the chromium family and the copper family. I'd like for you to try to go ahead and write the configuration for chromium at this time. So you've probably written out the following, ending with 4s2, 3d4. That is not the electron configuration for chromium. In fact, one of the 4s electrons jumps to the 3 and fills the final empty orbital. If we were to look at orbital diagrams in this case, we would see the filling occur as such, this being, of course, 4s, this being the 3d, and what you would expect based on this example here was that we would have 2 electrons in that orbital. But it's this electron that jumps out and fills this final orbital with a positive 1/2 upward spin. Why? Because this is a more stable, low energy form based on electron repulsion. I want you now to turn your attention to copper. Go ahead and think about what might happen with copper. Keep in mind the exception I have just shown with chromium. Indeed, the correct electron configuration for copper is ending in 4s1, 3d10, where we have that 4s electron jumping to fill the 3d10 slot. Again, this is due to the electron-electron repulsion that is occurring, and this has been shown to be energetically favorable and indeed the correct electron configuration for copper and chromium respectively. Now, I'm going to keep reminding you, is it 4s1, 3d10, or is it 3d10, 4s1? Experimentally, the latter has been shown to be true. But again, I'm going to leave it up to you guys in my class. Isoelectronic. This is a term that is used when two species have the same number and configuration of electrons. So let's look at calcium, for example. Recall when I first taught you about electron configurations. I never addressed configurations for cations and anions. I'd like to do that at this time. If you look at calcium, we're going to end with the 4s2. Now, You've seen so many Bohr models. We've talked about what is energetically favorable, what is stable, outer electrons, full valence. So in the cation form, which is calcium 2 plus, the calcium has given away 2 electrons. So if you were to write the electron configuration for the calcium cation, you would see that it looks like this, ending at 3p6. So those 2 electrons have been lost or given away. This is an isoelectronic form and it is the same or equal to argon. Now that prefix iso, as a reminder from our discussion on isotopes, is a prefix that means the same or equal. Argon and the calcium cation are isoelectronic. Now, I never said argon was calcium and calcium was argon. I simply said they're electrons. Because remember, it is the proton that defines and identifies an atom. In this instance here, the different number of protons is what determines what these are. However, their electrons are assuming the same configuration and thus are termed isoelectronic. Atomic radii may also deviate from expected trends. So let's look once again at this simplified version. I want you to look at the period with scandium, and let's look across all the way across to zinc. Now, what you'll see is that some appear to be decreasing, but others are about the same size, and some are just, you can't tell. Some even seem a little bigger. That is because when you're dealing with electrons in the D block, there is an unbelievably complicated set of interactions, not only going on between and among electrons, but between electrons and the nucleus, all right? There's a lot going on. In fact, this D block actually is a more compact block and exhibits some incredible characteristics in chemistry, such as magnetism. So it shouldn't be any big surprise with these complicated interactions going on why there are exceptions to trends in periodicity. This graph here, which is showing the atomic radii as a function of atomic number for many, many elements, shows graphically that there are exceptions. There are deviations from the apparent expected trends, and that's going to be true. Let's look here at an example. Let's look at vanadium and compare it to zinc. Now, I'm going to tell you that the atomic radius of vanadium is almost identical, if not the exact same in picometers as zinc. Yet, we have an additional 1, 2, 3, 4, 5, 6, 7 protons in the nucleus. 7 additional positively charged particles in the nucleus. You would think that there should be a considerably smaller atomic radius for zinc compared to vanadium. In fact, that's not the case. And again, this is due to these complex interactions that are occurring and electron-electron repulsion. Ionization energies also deviate from expected periodic trends. You've seen this graph of ionization as a function of atomic number expressed in the units of electron volts. And I alluded in previous podcasts, if we go lithium, beryllium, boron, carbon, nitrogen, and oxygen, what's going on here? Okay, well, that's one of those exceptions. And as I mentioned earlier in this video, oftentimes we will use electron configurations to elucidate these apparent deviations. Let's look at these two configurations and compare nitrogens with oxygen. So up top here, we have the electron configuration for nitrogen. Down below, we have the electron configuration for oxygen. Comparing these two, we see oxygen has this one additional electron. All right, and it's this one electron that will be easier for oxygen to get rid of. Oxygen has a lower first ionization energy because it has this single paired electron in the 2s subshell, which means the first electron to be ejected is the electron for oxygen and not nitrogen. Therefore, oxygen is being shown here to have a decreased ionization energy relative to nitrogen. It's those kinds of interactions that occur in chemistry that lead to these exceptions. Electron repulsion, once again, is what's causing this to occur. So oxygen will lose its electron easier than the nitrogen because of these repulsive forces. It'll have a lower ionization energy. Electronegativities may also deviate. All right, so let's look at copper. Copper is more electronegative than zinc. Copper is more electronegative than zinc. So we are right over here. And we can see these values on the Pauling scale of a 1.9 compared to a 1.6. Once again, we're going to turn to electron configurations to try to understand why this might be. With copper, we have a full D shell. With zinc, we have a full D shell and a full S shell. So why do you think copper may, anthropomorphically speaking, want to obtain or attract an electron more than zinc, even though it doesn't fit the trend that we're expecting? Why would copper have a greater electronegativity? The answer, copper wants to gain that one electron to fill the 4s. Zinc is full, so the next option for zinc is going to be the 4p subshell. Copper, on the other hand, needs one additional electron to be full. Therefore, copper has a greater electronegativity and a greater ability to attract bonded electrons. So I have gone over numerous exceptions that exist in electron configurations and periodic trends. I hope this helps, guys. I'll see you in class.